In this lecture, we discuss RC oscillators. Now, in the previous lecture, we discussed the LC oscillator. Now, LC oscillators we use for generating the high frequency signals. Now, here to generate low frequencies with LC, then L value, the size of L increases. That's why that creates the complication in the circuit, cost, size, everything. That's why we use RC values to generate the low frequencies. Now here there are two different types of RC oscillators are there. The first one is RC phase shift oscillator and the second one is Wien bridge oscillator. Now here this is the RC phase shift oscillator. Now in every oscillator the major component, major block is amplifier. Now here I am using one amplifier circuit. So for that I am taking one NPN transistor. Now here I am trying to draw the amplifier. Now I am taking the voltage divider biasing by using the R1 and R2 resistors. R1 and R2 resistor, I am using the voltage divider biasing. Now this is RC for the load current and RE for the negative feedback purpose and CE to bypass the AC signal to the ground. To ground the AC signals, this is CE, bypass capacitor to ground the AC signal, and this is the coupling capacitor, C out, and here I am taking the output. Now already we discussed in the LC circuit that this is an amplifier which will generate the 180 degrees phase shift. Now to generate the oscillation, there are two conditions we need to follow. One is A beta is equal to 1. This is Barkhasen criteria or condition for oscillation. A beta is equal to 1 and the second condition is theta. So total loop phase must be 360 degrees or 0 degrees. 0 degrees. Now in a LC circuit we have seen that CE amplifier is producing the 180 degrees and LC tank circuit is producing the 180 degrees by making ground in between two inductors or two capacitors, so that tank circuit is producing the 180 degrees phase shift. Thereby it is satisfying the Barkhasen criteria and it is generating the oscillation. Now coming to the RC phase shift oscillator, here we are not using the LNC values, tank circuit we are not using. So now how to produce? Now we are using the amplifier. This is a CE amplifier. CE amplifier produces the 180 degrees phase shift and one more 180 degrees phase shift should be produced by the RC components. So now how to generate that, now we will see. If I take one R and C, if two components I am taking, if I apply a sine wave to this circuit at the output, now if I take output over here, then it will give the 90 degrees phase shift. Now if this is my input, then at the output I will get 90 degrees phase shift like this. So now this RC values will produce the 90 degrees phase shift. That phase shift we can calculate by using theta is equal to tan inverse 1 divided by omega RC. So this is the how we can produce the 90 degrees. Now if we want 180 degrees means what? Such RC values we have to take 2. Now RC, one more RC network if we connect, then it will produce the 180 degrees. Now if we try to recollect the phasor diagrams, in your first year you have studied the phasor diagram, right? If I am taking one RC, if this is the R, L, C network, and for this if we apply the sine wave, and in this the current is I current and the voltage drop across R, C and L, how the voltage phase with respect to I means, now if this is the current flowing in that, then the voltage across the resistor is in phase with the current and the voltage across the inductor is leading by 90 degrees and here this is a 90 degrees, and similarly the voltage across the capacitor is lag by 90 degrees. Now here you can see here that the voltage across the capacitor and resistor is how much? 90 degrees phase difference is there. Now by using R and C we can get the 90 degrees, but this 90 degrees is only for the theoretical purpose. Practically it is not possible. Why? Because so if we are taking a capacitor or inductor, every capacitor and inductor is having some internal resistance, thereby it will not produce the 90 degrees. So less than 90 degrees is possible. Now in between any value can be possible by taking one R and C values. if you substitute, now here if I wanted 60 degrees, now take 60 degrees and assume, take one value, capacitor value or resistor value, because capacitor values are fixed values, we don't get the all the values. That's why now here we need to assume the take the one capacitor value, and from that need to find out the R value, then we can construct this circuit, R and C circuit, like that. Now if 90 degrees is not possible, means what, next angle is what, 60 degrees. So now 60 degrees, such a 60 degrees, how many circuits are to produce the 60 total 180 degrees by using 60? So we need 3 R and C circuits. So by connecting 3 R and C circuit, we can produce the 180 degrees. Now if I take 45 degrees, then such RC networks we need 4. So by using 4 we can generate the 180 degrees, but good engineer always try to minimize the number of components. That's why we go with the, so 90 is not possible. With the 90 only 2 RC circuits are sufficient, but that is not possible in practical. So that's why we are going for the next one is what, 60. But 45, 30 also we can design, but there the number of components are going to increase, thereby the cost also, cost, size, everything. So that's why now here I am using the 3 RC networks to produce the 180 degrees. So now here if you see one capacitor R, RC net, one more RC network, and this is the third C. Now this is C, R. Here if you see, this is the one RC network, one more RC network, here only one C is there, R is missing. So this R is coming in parallel with the voltage divider R2 value. So both, what is the equivalent resistance we have to calculate, and that value here we need to put actually. So this is the R equivalent. So this R equivalent is nothing but what, R2 is coming in parallel with the R. So both R2 value and R value both are coming in parallel. So instead of connecting 2 resistors, what is the equivalent value, we have to calculate that, and we need to connect that resistor value over here. Now this is the RC phase shift oscillator circuit diagram. Now if we try to derive the expression for the frequency, then the F is equal to cutoff frequency, or F, the oscillations produced by this circuit, F is equal to 1 divided by 2 pi RC root 6, or you can take root 1 divided by 2 pi RC 2n, where n is the number of RC networks. Now here it is 3, so 2 into 3 is equal to 6. That's why I have taken the 2 pi RC root 6. So if you wanted to go with the 4, 5, like that also you can go, but this is the minimum number of components we are using with the 3 RC networks. That's why the formula for this is F0 is equal to 1 divided by 2 pi RC under root 6. Now if we try to calculate the gain for this for this circuit, the gain must be greater than or is equal to 29. Then only this circuit will produce the oscillations. So this is about the RC phase shift, but what are the drawbacks of this? By using this we can generate the low frequencies, but drawback is, so we can't change the frequency value. Now if you wanted to change the frequency at the output, then you need to change the R and C values. If you are changing the R and C values, then the phase shift, now here it is tan inverse 1 divided by omega RC. So here it's now if we are changing the R and C values, here it will not maintain the 60 degrees, that's why it will not produce the oscillations for the various ranges of frequencies. Now by using this we can generate the low frequencies, but for which circuit we are designing, only for the few values we can change, but not for the maximum range. If we wide range, if we need wide range of frequency, then we need to go for the Wien bridge oscillator. One more RC oscillator is Wien bridge oscillator. And one more drawback is, when we are changing the R and C values, the gain of the circuit also changes, thereby it will not produce the oscillations. These two are the major drawback of RC phase shift oscillator. That's why we are going for the Wien bridge oscillator. Now in a Wien bridge oscillator, here we are using one bridge. So a bridge itself, it is not generating any phase. So that's why we need to use two amplifier circuits. So one CE produces the 180 degrees and one more CE produces one more 180 degrees. Why? Because now here the bridge is not producing any phase difference. Now this is the amplifier, first amplifier. So R1, R2 voltage divider we are using and RC1. And one more amplifier I am connecting using the capacitor. So this is called the capacitor coupling, RC coupling also we can say. RC2, and here also I am using the voltage divider biasing. R1, R2 already over, R3, R4 I am taking. Now here I am connecting the RE value and bypass capacitor. Now here I am taking one coupling capacitor. Here I am taking one bridge circuit. For that one R and C values are in series and one more R and C values are in parallel. So this is called the lead lag circuit. This lead lag circuit is connected to the base of the transistor 1. This is the amplifier 1, this is the amplifier 2. Now here we are not connecting any resistor. So here instead of connecting the resistor, now this value we are taking from the bridge. Here one resistor and one more resistor, this is connected to the ground. Now instead of resistor, here we can take the tungsten lamp. If any temperature variations are taking, so to get the more stability at the output, we can take the tungsten lamp. Now here this from the output we need to give the feedback, means what? Output we have to apply to the input. Now here we are taking the output. So output I applied to the bridge. Now in the bridge we are using the one RC series circuit, R1 C1 series circuit, R2 C2. Now already I have used R1 R2, let it be. So I will change the names of these resistors. Now here R1 R2 already used, R3 R4, R5 you take and R6. Okay, this is the Wien bridge oscillator. We are using two CE amplifiers to produce the 360 degrees. Now one CE will produce 180 degrees, one more CE will produce one more 180 degrees, thereby it is producing the 360 degrees. Now output we have given to the bridge. Now this bridge, in this we are using one lead lag circuit. One is producing the phase, another one is cancelling the phase, thereby here in this bridge we are not getting any phase. So here it is satisfying the 360 degrees phase concept, and now here the gain should be greater than or is equal to 3. Then only this complete circuit will produce the oscillations. If we derive the frequency, then the frequency formula is equal to 1 divided by 2 pi R1 C1 R2 C2 under root. So if R1 is equal to R2 is equal to R, and if R1 is equal to R2 is equal to R, and C1 is equal to C2 is equal to C, then the same expression F is equal to, how can we write? 1 divided by 2 pi RC. Now this is the frequency formula for the Wien bridge oscillator. Now in this, by varying any one of the component or two components, R1, R2 or C1, C2 or any one of the component, by varying we can generate the wide range of frequencies at the output. So this is about the RC phase shift oscillators. Thank you.